Hi guys. Hi August. Okay, welcome back to another episode of Introduction to Computer Networks. This is Polly streaming the second last time this semester, and again from NTU. So let's check out the announcements first. This is week 15. We are just 2 weeks away from summer. Yay! Okay, so just hanging there. Okay, this weekend, the final week. This week, we will still have 7 to 8 quizzes due, and no worries, 2 of them are straightforward. And there are 4 of these, 50 to 53. They are in a series to make a very important point, which is BGP routing is policy based. And we might not have time for quiz 56. We'll see. Now, next week, okay, we have planned for a lecture next Tuesday, but let's cancel that, all right? And Polly will be online. So I'll be on Discord and Google Meet in case you have any questions. And please take advantage of the time to study for the last exam, all right? And exam 3 here, okay, so the scope is final. So if you click into the exam 3 channel, you will see the scope for exam 3 will be PA number 8 to 9, the entire chapter 4, chapter 5.1 to 5.4, which means that we cover all the way to the internet traditional routing. We'll not cover the modern routing, the SDN based control plane. But there are videos available about the SDN control plane in case you're interested. Okay, this semester I chose to cover the link layer to some degree, so you see a little bit what the link layer protocols are doing. Okay, so we'll be covering chapters 6.1 to 633 for the final exam, and this is going to be in the lecture tomorrow. Good. So that's all I want to say before the lecture starts. Now let's check out the topics. Today is going to be all about BGP. All right. If you recall from last week, we've already played an introductory video of BGP. In that video, you saw a little bit distance vector routing. Okay, is very similar to BGP. In distance vector, we have this endless loops of 3 steps, remember? Yeah, collecting distance vectors from the neighbors, doing the Bellman-4 computation, and then distribute the new distance vector to the neighboring routers. In BGP, in that very last video last week, you saw, hey, it's also an endless loop, isn't it? It's an endless loop of now 4 steps. Okay, the first step is collecting reachability information from the neighboring ASs. Hey, very similar to distance vector, right? In distance vector routing, we're collecting what distance vectors, which is also the reachability information to arbitrary destination, isn't it? So, first step, similar to distance vector. Now, the second step is a little bit interesting. In BGP, the second step we do is to distribute this reachability information to the routers within the AS. So we collect reachability information from outside the AS, and we distribute also further to the internal routers. And this is necessary because if you recall the inter-AS routing overview, you see that in a router, whether this is an inter-AS router or intra-AS router, to build a forwarding table, we need to know information about the intra-AS routes as well as what? The inter-AS routes. Okay, so the second step is to let BGP inform the intra-AS routers what the inter-AS routes are. So that is the one extra step. The third and the fourth step will be similar. The third step is to determine routes. And the fourth step is, hey, once we discover the new inter-AS routes, we propagate the new inter-AS routes to the neighboring ASs. All right, so that's a quick overview of BGP. Today, we'll play the second video of overviewing BGP. So in this video, you will see that Polly talking a little bit more about the reachability information, okay, and the eBGP and iBGP connections used, okay, to send the reachability information across ASs and intra-AS. Okay. Now in the second half of this video, you will see an example, okay, when a when a destination network starts announcing its own existence and how that information, okay, to reach the destination is propagated to the destination's neighboring ASs, and the neighboring ASs will pend themselves to the path and further propagate, okay, the AS path, the reachability information to the destination, to the neighboring ASs of the neighboring ASs. Okay, so that is what this video is about. One last point to make is just this: the reachability information, aka the path vector. When they travel across the border, go from one AS to another AS, this is actually part of the exterior BGP protocol. So in exterior BGP protocol, we establish the exterior BGP connections to allow path vectors travel across borders from one AS to another. Now for path vector, that is supposed to be sent internally to all the internal routers, then belongs to the iBGP protocol, and they are sent through the interior BGP connections. And these are actually illustrated using this picture here. Okay, so if we focus on AS2, we do have two gateway routers, 2A and 2C. So you see these gateway routers connecting to other ASs. There are exterior BGP connections to outside, exterior BGP connections to outside. So eBGP, in red color. But in addition to that, 2N and 2C both need to send path vectors internally. Okay, so you see they went through the iBGP connections. All right, so iBGP connections in blue. So once again, these are gateway routers, and the gateway routers you see having both the red connections and the blue connections. They run both the eBGP part of the protocol as well as the iBGP part of the big BGP protocol. Those BGP connections are often referred to as the BGP sessions. So these routers will exchange messages over semi-permanent connections. The reason that they're called session is probably because it's semi-permanent, so it's on all the time, and occasionally you take it down and then restart it. Okay, so semi-permanent TCP connections. Now, TCP, BGP is a routing protocol, right? These messages we send should be at the layer 3, but TCP is actually a layer 4 protocol. Okay, how do you like this? On the other hand, TCP allows reliable data transfer. So would you prefer the path vector? So these messages that we're exchanging between the BGP routers, the path vectors being sent reliably or not? To push it a bit further, what about using TLS, okay, the secure version of TCP? And if we use TLS, these BGP messages, these path vectors, would look more like an application level message. You think about it, you debate within yourself. Now, the messages we're exchanging between the BGP routers over the BGP sessions are these. The path to all sorts of destination networks, the path to all sorts of destination ASs. In fact, altogether, we just call it the path vector. Okay. So BGP, again, a path vector protocol. And let me give you an example here. So let's say in AS3, okay, there is a prefix X. And this is the destination for packets coming from maybe AS1 or AS2. So AS3 that learns about this destination will need to announce, okay, advertise it to outside of AS3. So 3A here, okay, will need to announce, okay, its existence and pending its own AS number, so AS3 here. So this will be the AS path, okay, being advertised. This will be the AS path being sent in the BGP message to the other end of the exterior BGP connection, to the other end of the BGP session. So 2C here, okay, will receive the AS path, AS3, X. So AS3's gateway router 3A will advertise the path, to AS2's gateway router 2C. So when AS3 does this, it's also saying that AS3 promises AS2 to relay packet, okay, on behalf of AS2 so that it can reach destination X. Right? All right, so with that video, now you see what we meant. Reachability information is essentially the pass vector, and pass vector is stored in this message called the BGP advertisement. Now, in the next video, you will see in this BGP advertisements, it contains not just the pass vector, but a few other information. And you will see also that after the gateway routers of an AS receive these pass vector from the neighboring ASs, there'll be some decisions these gateway routers need to make, whether they would import certain pass vectors, and whether after they append themselves to the pass vector to further export the extended pass vectors to the neighboring ASs. Okay? And this import, export are called the import-export policies, and you see a little bit that BGP is a routing protocol that's mainly based on policies. Let's say more about the messages we exchanged in these BGP sessions. So these messages are essentially pass vectors. Inside the pass vector, we have lots of these pass entries, okay, or route entries. Each pass in the pass vector of BGP is this: the destination address. Now, because in BGP we are sending packets to a destination network, therefore, to address to a destination network, we use the prefix of the destination network. And then attributes. Now, in pass vector, the most important information there is the path. Therefore, you see, okay, in the set of attribute here, we need to definitely have the AS pass. So AS pass is the most important component in the set of attributes. There we see the list of ASs, okay, it takes from the source to reach the destination. Now, the discovery of the list of ASs, the discovery of the AS pass, however, okay, came the other way, from the destination network. Okay, so the destination network is going to advertise its prefix, okay, and so that's going to be in an advertisement message. Okay, so the whole AS of the network X, okay, let's say AS2, okay, receiving such an advertisement at the gateway router, okay, that gateway router is going to prepend itself, okay, prepend the AS number, okay, AS number 3, okay, before X, and send this out as the prefix advertisement to the neighboring AS. The neighboring AS, let's say AS2 there, receiving such, okay, an advertisement, it's going to prepend itself before it sends out further to AS2's neighboring AS. Okay. So now AS2's neighboring AS receiving such an advertisement will then discover, right, a path to go from AS2, AS3 to destination X. Okay. So list of ASs through, okay, these paths, the prefix advertisements as traversed. Okay. So that is the AS path. One and the most important, okay, part in the attribute set. Second important is this, the next hop. Now this is not quite, okay, the next hop AS, the next AS number, okay, in the AS path. No, it is actually the gateway router, okay, within the source AS that is directly connected to the next hop AS. So it's carrying the IP address, okay, of the gateway router, leading to the next hop AS. So the two together necessary forming the attribute set. Now, BGP routing, okay, has grown more and more being policy based, okay, meaning the gateway router, they're receiving these prefix advertisements. Okay, it's not like for every advertisement they will actually prepend its own AS and then pass it down further to other neighboring ASs. There'll be some sort of import policy. Okay, so the gateway there receiving the advertisements will have to say, okay, will have to decide. Some of the advertisements they will decline, and some others they accept. Only the ones they accept will be propagated further to all the routers within the AS. Okay. Now the gateway routers, okay, in the AS receiving these accepted, okay, advertisements will then decide whether to prepend themselves and then pass the expanded advertisements, okay, to the other neighboring ASs. Okay. But you see, there are also policy, okay, the AS might apply before these other gateway routers, okay, advertise the expanded, okay, AS pass to the neighboring ASs. Okay, so some of them actually might have complex policy that is very fine-grained. For example, if one gateway router, okay, connects to two other neighboring ASs, this gateway router might say, I send this particular extended advertisements only to one of the ASs. Yeah. Policy to import and policy also to export. All right, so just keep in mind when you see an AS pass, the first one indicates the next hub AS, and the last one is always the destination network, which is represented by the prefix, the network IP address prefix of that network. Okay, good. Now, the last video to overview BGP are just two more examples of BGP advertisements being propagated through a network. First example, easier, and second example, you see a little bit of complexity. Let's go over a couple more examples so it's more clear where the import policy and the export policies are applied. So this is the same example we saw earlier. Destination network is here, X, okay? And so AS3 there is gonna send the pass advertisement. Okay, that looks like this, AS3, comma, X. Okay? And this is gonna reach 2C of AS2. So AS2's router 2C receives pass advertisements like this. And this is through the exterior BGP connection. And the advertisement came from AS3 and from router 3A. So 3A of AS3. Now, yeah, if you recall in the very early slide, right, the border router here will then propagate the AS path throughout all routers in the network. But no, there's import policy. So yeah, the exact process is more like this. 2C there will actually check AS2's import policy. If the policy says 2C, it's okay to accept the pass, then 2C propagates the pass to all routers internal of AS2. Okay. So sending of these AS pass internally is through the interior BGP connections. Right? So the import policy actually happens before the propagation of the pass, okay, to all the routers internally. And then, okay, 2A here, receiving such a pass, can then prepend itself and pass it further to the neighboring ASs. But wait, yeah, the export policy is applied here before passing on of the advertisements. Yeah, let's check. If 2A here is allowed to advertise the discovered pass to AS1 here, okay, then we form the new advertisement AS2, AS3, and X, and then send it to 1C that belongs to AS1. Okay, so once again, before the prepended, the extended AS pass can be advertised further to the rest of the internet, we check the export policy. Right? Second example is a bit more realistic. So 3A here, the gateway router of AS3 might have multiple eBGP connections to outside. Okay, so in that case, a gateway router might learn multiple paths to a destination in AS3. So let's see. One of the paths is this, right? AS3's 3A sends AS3X, okay, as an advertisement to 2C. 2C checks the import policy and therefore pass it on to all the routers internally. 2A picks it up, checks the export policy, and let's say that it's just allowing advertisements of the pass further. So prepend AS2 to the pass and then send it further. At this point, 1C learns the pass AS2, AS3 to destination X. And the way to go is for 1C to send to 2A. The other direction is this. 3A can be simply sending what? AS3X, okay, this past advertisements directly to 1C, and 1C will just simply learn, right? There's another way to reach destination X, which is just simply sending it to AS3 through 3A. Okay, so these are the gateway border routers that 1C send the packets to. okay, for the two different paths, 2A and 3A. At this point, 1C sees two advertisements coming in. Yeah, before 1C propagates any of the paths further, okay, it needs to check the import policy. Okay, so A is one's gateway router, 1C there. Okay, we need to choose. It could choose one of the two, or it could just take both of them. Okay, let's say that 1C chooses AS3, comma X. Yeah, sure. The shortest AS path, and advertise it to all routers internally of AS1. Okay, this is the second example. All right, so you get the idea. When an AS okay, okay, welcome. When a BGP router receive an AS pass advertisements from the neighboring ASs, they will what? Check import policy, right? And propagate further. At the other end, before we export, we prepend our own AS to the pass we received and then decide to send it further. Okay, so that is the idea of path vector routing. Okay, so it's not exactly like the distance vector routing. Okay, it's not exactly like the distance vector routing also that deciding where to send the advertisements or accepting advertisements is policy based. Okay, policy based. So that is the tricky part. We'll spend some time later today and early tomorrow to go over this policy thing. And you will see a little bit that it's a very human-centric decision. Okay. And before that, let's get into the detail of BGP and particularly about how we set up the routing table for an internal router so that the internal router will know if the destination is somewhere outside of the AS, where to forward the data. Okay, so this is what the video is about. Let me borrow example 2 here and continue to talk about this. How a router sets up a forwarding table entry, okay, for a destination outside of the AS. Okay. Yeah, scenario the same, destination being X. 3A, the gateway router of AS3 has 2 eBGP connections, therefore 1C here potentially can receive 2 AS paths. And 1C, according to example 2, chooses the shorter AS path. So let me run the animation. So 1C discovers 2 paths and picks the shorter path. Okay. And this shorter path is further propagated internally to all routers. So 1A, 1B, and 1D will learn about the shortest path to destination X from 1C. Okay. And what 1A, 1B, and 1D will do is, well, if I receive ever any packets with destination X, then I will forward the packet towards 1C, the border router, okay, they receive, okay, the AS path from. Okay. Now, to make it easier to explain what's coming up next, let me just label, okay, for 1A, if the packet is supposed to go out on this interface, then we call that interface 1. And yeah, for packets to go out on this other interface, let's call it 2. Okay, similarly for 1D, this is interface 1, this is interface 2. Now, 1D here, okay, has discovered there is a path to destination X that is going through 1C. Okay, that is what 1D knows so far. To add an entry into the forwarding table for X, 1D needs to know exactly which interface, is it 1 or 2, that leads to 1C. How would 1D know that? Yeah, call the intra-AS routing there. Okay, let's say it's OSPF. Okay, so OSPF is going to tell us if the destination is 1C, what is the link, okay, along the shortest path to 1C. Okay, so that happens to be 1, so we will fill this entry here. Okay, interface column being 1. Similarly, let's try to derive again for 1A. Okay, so 1A knows, for destination X, I should be forwarding packet towards router 1C. So let's call intra-AS routing and find out from OSPF, what is the shortest path to 1C and which link, is it 1 or 2 on the shortest path? And we'll get 2 here, and 2 here with 4 packets to 1D. And 1D here we see earlier will be forwarding packets over this direction and reaching 1C. Therefore,
going backwards and reaching destination X.
All right, so that was the simple example because in AS1 there's only one gateway router, right? So all the internal routers just need to send the outgoing interface towards that gateway router. Next video, you will see a more complex case where in a domain you have multiple gateway routers, multiple BGP routers, and multiple AS paths to the same destination. Okay, how would the internal router decide which interface to send the data in such a case?
Route selection. Now, this mechanism is necessary for slightly more complicated scenarios. Let's go back to example 2 again, right? We have this router, 1C, being the gateway router of AS1. So you see towards the end of the scenario, AS1 discovers 2 AS paths, one from AS3 to go to destination X, the other from AS2, and then via AS3 to go to destination X. So in the previous slide, we say the policy of AS1 is such that we only select this to import. And so 1C propagates this AS path to all internal routers. Internal routers will then send packets, destination being X, through 1C and therefore being forwarded to AS3. Very simple. But what if we relax the import policy a little bit further so that 1C here cannot discard this other AS path? As a result, 1C will need to propagate both paths internally. So each of these routers internally will see more than one route to the destination X. Ouch. Yeah, so that's when we apply the route selection. So internal router there will need to apply route selection here to decide which of these two it will send packets to. The process is like this. Step number 1, check the local preference of these routes. So if you recall earlier, a route is what? Composed of the destination network's prefix and a set of these attributes. So we know that AS path is one attribute. Next hop is one attribute. There's one more attribute called the local preference. So this one actually weighs the highest. So BGP actually checks the local preference first and take the path with the highest local preference. So local preference there is usually to indicate, between the two neighboring ASs, AS3 versus AS2, does AS1 prefer forwarding packets to AS3 or AS2? So if AS3 is preferred, AS3's path, so this guy here is going to carry a higher local preference. Now, if there's no local preference specified, then we go to step 2. So the internal router, let's say 1D here, will then check which of these multiple paths to destination X give us the shortest AS path. So in the scenario, 1D is going to pick this one. Now, if both AS paths have the same path lengths, then we go to step 3. We pick the closest next hop router. 1D here sees 2 paths. The next hop router for this path is going to be 1C. The next hop router for this path here is going to be 1C as well, because 1C is the border router receiving these advertisements. But if you consider a slightly different scenario, so again, we have AS3, AS2, and AS1. And so the router now in the limma is now 2D. 2D here actually sees 2 AS paths. One AS path is actually coming from 2C. 2C is the gateway router connecting to AS3, which it receives a path to X, AS3, X. 2A is the gateway router connecting to AS1, where AS1 is passing another AS path to AS2. That is AS1, AS3, and X. So 2A passes this path to 2D. 2C also passes on this path to 2D. So 2D in the end learns, there's one AS path through next hop to A, this guy. There's another AS path through 2C, this one. 2D here Okay, assuming that abandon the shortest AS path phase, go straight to the closest next hop router phase. Then we'll do this. For this path, next hop router is 2A. For this path, next hop router is 2C. 2D here will consult, okay, the intra-AS routing again to find out is 2A closer or 2C being closer. So if you see the scenario, 2A distance to 2D is only the link cost between 2A to D, which is 201. Distance between 2D to C, however, is 263. So 2D here is going to choose 2A to forward the packets to. So it's going to choose AS1, AS3, and X, this other AS pass, which is actually longer, okay, than this other one to pass the data. This is also very well known as the hot potato routing. Allow me to explain. Yeah, so 2D is this guy holding a hot potato. So yeah, the packets are almost like these hot potatoes, and 2D can't wait to get rid of these packets. So 2D wants to be able to pass the hot potatoes, the packets, as soon as possible. Therefore, picking, okay, this poor guy here, 2A, to throw all the hot potatoes over. Okay, distance is shorter. Okay.
All right, and that takes us to the first quiz today. So this is quiz 49. All right, so this is the same example you saw in the video, except here, Polly added a link between 2A and 2B, and the link cost is 27. Okay, so 2D here needs to send data to destination X, and 2D learns two paths, right? From 2A, we learn this path. From 2C, we learn this other path. So again, let's set the local preference to skip the AS path length check and go directly to the closest next hop. Okay, then tell me, which router would 2D send the data to next? And which AS would the data go next after exiting AS2 here? All right, now let's go to the score space. Channel W15, quiz 49. Guys, you guys have 4 minutes. All right, if you pay attention to the video, this should not be hard. All right, let's start counting time. Okay, so in the end, you guys need only like 30 seconds. Yeah, so I see. So it's quite obvious, isn't it? So let me clear the dribbling here. It's quite obvious, right? We then take the BGP router that is the closest. Okay, and which one is that? From 2D to 2A, shortest path. 179, I think. And from 2D to 2C, the shortest path is 264, 263. And this one is obviously the shorter one, and therefore data goes to 2A. Ah, okay, I guess 2D. Yeah, so the next router, data will eventually go to 2A, but the next router is 2B. Very good. Okay, August, I think you get the idea. It will eventually go to 2A, but it will go through 2B. That is the shortest route. So, very good. I think that's what you meant. I think that's what you meant, August. Okay, but 2B, which router is the next? Okay, that will be, okay, 2B. So, very good. And the next AS, of course, if we send it eventually to 2A, the next AS is AS1. Good. That is the hot potato routing. Okay. Awesome. The BGP router we want to go to is 2A. But you see that according to OSPF, the shortest route is 2D, 2B, then 2A. Okay. So to be technically correct, so maybe I should, yeah, I just say which router, okay, do the 2D send the data to next, okay. Yeah, so Aslam, to be 100% correct, it should be 2B, all right? But it's okay. I'll accept 2A. Yeah. So between 2A and 2C, of course, it's 2A. Very good, guys. This is called the hot potato routing, okay? So essentially the data is the hot potato, and the sender here is trying to hand that over as soon as possible to the BGP router that is the closest. Okay, now you get it. So this only happens when the routes are a little bit complex, that you have multiple paths and you have multiple BGP routers handling different paths. Good. All right, so you see a little bit of complexity there in BGP routing. And the last video about BGP is the messages. Until now, these AS paths are stored in this BGP advertisements. This BGP advertisement is not the only type of messages being transmitted between these eBGP or iBGP sessions. There are actually 3 more types.
This is the last slide of the BGP protocol. Okay, so in BGP, the protocol, it actually defines 4 types of messages. Okay, so not just the message we mentioned earlier containing the pass factor being passed in the BGP sessions. Okay. There are other types of messages that BGP sends. So some of them are actually to send the pass advertisements, to send the pass factors, but some of them are to establish the TCP connections, okay, for the session, or to tear down the TCP connection, or to keep the TCP sessions alive. Okay, let's go through these BGP messages. The first type is called the open message. Yeah, the first purpose of it is to establish the TCP connection. Okay, so the sending peer there will be sending an open message to the receiving peer. Okay. Receiving peer will be sending back an ACK for that message. As a result, the 2 peers establish a BGP session. So the ACK of the open message there is going to be in the keep alive message format. Okay, I know it's a bit tricky. Now, the open message is also used to do the authentication. Okay, so the 2 peers can authenticate each other to make sure that the pass advertisements, okay, are indeed the true pass, okay, to be discovered. Now, update message. So this is the message being used to send the pass advertisements, the pass factors. So this message is also allowing the routers to withdraw outdated pass factors. Keep alive message we saw earlier, it's to ACK the open message to establish a TCP connection. Keep alive message is also being sent, okay, periodically to refresh the TCP connection, just in case there's no update messages being generated. So update messages is, yeah, the past advertisements. Last is the notification message. Okay, so this reports in case there's any error in the previous message. Okay, and it's also used to close the connections for the peers.
All right, now a pop poll. Okay, which BGP message is the BGP advertisements? Do you recall? Okay, let me know. All right. Okay, August. Fast and correct. Yeah, the update messages. Great. Yiting, Yuling, Ali, Jiaxuan. Great. So the update BGP messages is the official name for these BGP advertisements we've been talking about. Okay, very good. And so now let's talk about policy, the human side of internet routing. Okay. Now, this video, unfortunately, a little bit long, but it's okay. We'll probably play this video and see if we have time for quiz 50. Chances though that we have time for quiz 50. In this case, then we'll go through quiz 50 to 53 tomorrow. Okay, so make sure that you attend early tomorrow. right? So it's a little bit long, but you will see some examples, okay, of certain domains will not be happy to forward the AS path, okay, to other domains or forwarding data for the other domains, okay. Yeah, so it's a little bit like, you like me, but I might not like you thing.
One very important issue about BGP to discuss here is, BGP routing is very policy based these days. If you recall, there's import policy, there's export policy, there's also local preference for route selection. Yeah, there are lots of things the network admins can tweak, okay, to decide where packet goes. The reason for those policy-based setting is this. Let me use an example to explain. Consider this network. We have three ISPs in the middle, ABC, they are the provider networks. W, X, Y are the customer networks. More specifically, W is the customer of ISP A. So W pays A some amount of money every month, and A will in turn help W passing packets, okay, going out to the rest of the internet or coming in from the internet. Similarly, if the traffic is supposed to go out the other direction, right? So W pays A, and therefore A is responsible to serve W. Similarly, for this customer-provider pair, Y being a customer, C being a provider, X being a customer, B being a provider. Now, X is a little bit more complicated. It's multi-homed, okay, customer network. So X here pays B and C. Okay. As a result, B and C should both be forwarding packets for X. In scenario 1, let's assume that there's a user in customer network Y here wanting to send something to the user in W. And so in order for W to draw in traffic from the internet, its provider A here will need to announce its existence. So AW here, okay, an AS pass needs to be sent to the neighboring ASs, which happen to be ISP B and ISP C. Okay, so A advertises pass AW to B and to C. As a result, okay, B is going to see this pass, okay, and prepend itself, okay, and see if this AS pass needs to be further advertised to yet another neighboring AS, such as provider C. Now, B's network admin actually knows better and choose not to do that. And the reason for that is because of this. If BAW is advertised to C, C is going to discover, this is actually one way for this user in Y to send traffic to user in W. And therefore, the traffic is going to go this way to W. And you know what? B here, okay, B does have a customer X. X is paying B. But is W paying B? Is A paying B? Is C paying B? Well, based on the setup of the problem, WAC not paying B, and yet B is using the network resource here to transit the traffic for B and C. Okay, so B gets no revenue to do this route, BCAW, because CAW, based on the scenario setup, not paying B. Okay, so chooses not to advertise BAW to C is so that C does not discover this path, and therefore, okay, not using this path to send traffic. Instead, C here receiving AW is going to prepend itself CAW, and Y is going to use CAW as a way to send traffic to the user in W. So you see in this scenario, very obvious. For a customer network, ISP will be happy to route traffic to and from the customer. Okay. But the ISP not getting paid by others would hate to transit traffic between these other ISPs. Okay. So bottom line, not getting paid for the work. Scenario 2 is very similar to scenario 1. The network is completely the same, and we just continue scenario 1 from here. When B has discovered BAW is a path to go from B to W. Now back in scenario 1, a min of B chooses to not forward BAW to C. Okay? so that we don't draw traffic this way. Nice. But B will actually have to send BAW to X. So X can discover XBAW is a pass. So just in case there's any user in X wanting to send data to user in W. Nice. So makes sense. But hey, X is dual home, so there's yet another connection to a neighboring ASC. So should the network admin of X here send XBAW to C? Well, let's assume that we send XBAW to C. In this case, C is going to discover CXBAW is a pass to send data to W. Similarly, Y is going to discover YCXBAW is a pass to send traffic. YCXBAW is a pass to send traffic from a user in Y to a user in W. And that's going to travel like this. How do you like this? Well, from an X's network admin's point of view, hey, this traffic is actually not for me at all, right? It's actually between Y and W. Y pays C, W pays A, and no one is paying me, and yet I'm paying B and C. Okay, so it's a big no-no for X here to send XBAW to C. All right, so X will not want traffic coming from C and simply transiting to B. So X should not be advertising anything to C, okay, coming from B. So again, money is the issue, all right? So X is not getting any money from C or from B. Therefore, X is not happy transiting traffic for these other ISPs or even from other customer networks not paying. Okay?
Yeah, so guys, have you had the situation that your friends keep asking you for favors? But then, okay, after a while, you don't feel like helping anymore because they never really help you, okay, with other things. Exactly, okay. When a customer network asks a provider to try to transit traffic for them, they pay the provider, okay. So the provider will be happy and like the customer, but the provider might not like to transmit traffic for the other provider's customers, you see. Okay, so that is the nature, unfortunately, of BGP routing now on the internet. Okay, and given the time we have, I would suggest that we end the lecture today now and start tomorrow morning from quiz 50. Okay, and it's a series of quizzes to demonstrate that it's really tricky. It's really tricky. And with that said, I say goodbye. Okay, that's all for today, and see you for the last time tomorrow. There. Okay, bye. Yeah, guys, feel free to look closer into quiz 50, and it's also posted on the Discord channel W15 quiz 50. Okay. So if you feel like posting your answer, it's okay. Okay, Polly has not yet explained it, but feel free to try to post your answer. All right, guys, see you tomorrow. Okay.